So you want to make sure is that you don't fish to the point where we have reductions in stock. So if we fish somewhere in here, we should be fine. But we're missing a key piece of information. We don't know the revenue or the cost of the particular fishery. So what would you say we do this time? What should I change to get some economic information in here? If this is the harvest and the growth, this is Q, right? What can I multiply by Q? E? Okay. We can get a revenue function to see how the correlation between the stock, the population, matches the change in the value of that stock. So let's do that. We can, sort of restricted using this word. Put it over here. ER. So redo the graph one more time, and we put dollars here. All you have to do is change growth to dollars. And we have the stock here. So this would be the maximum value of the sustainable yield. And this now becomes revenue. We can also do one more thing. We can change this to effort, right? Instead of actual fish, think about it as fish caught. So we take the stock and then change it to stock caught. If you do that, then we have effort. So every day you go out to catch fish, there's a cost to that. So we can put effort down here now. We just change a few things to be able to add the economics. So then this becomes, instead of the growth of the fish stock, this now becomes the effort revenue function. So let's get rid of this one. So now we've got dollars and we've got effort, which relates to the quantity. So this would also be the cost of fishing days. You know how much it costs you per day to fish. So this would be linear. Now we want to add the total revenue. Oops, sorry, losing my marbles. Total cost. So you know how many days you're going to fish, how much effort it takes. Every day you go out, you know what the cost is. So that's going to be a linear function. And we wind up with something like this, total cost. So it's a little bit different of an approach I'm using with the fisheries than with forestry. We looked at marginal revenue product, the change in the value as the stock grew, as the forest stock grew, and then compared that with the value of time. In this case, we can take the stock of the population, the physical resource, and look at the cost in terms of the effort to catch it. The same works, we could change this picture to hunting or something, and the same would work. So you've got effort, and since we have dollars here, we know that every day you go out is going to cost you more and more and more, okay? So if you fish for 10 days at $1,000 a day, $10,000. It's a linear function. So at this point, what can we say about harvesting? Where should we harvest? how many days should we fish? Okay. So we want to know the effort. This is revenue, right? So we've got revenue and we've got cost. What can we say about where we should, how much effort we should put in?
As much
As much as we can? Oh, then you're saying we should be down here. That's the maximum effort, right?
When marginal cost is equal to marginal revenue.
Right. Where marginal cost is equal to marginal revenue. Where is that on here?
On the top of
Here? Probably not. But you're right, it's where marginal cost equals marginal revenue. What about this point? Should I harvest here?
Is that equilibrium?
What's true at this point? This is total cost, and this is revenue.
That's for, isn't it equilibrium?
Profits would be zero.
No?
Or,
Who said what?
Profits would be zero.
Profits are zero here, right? I don't want to harvest here. The total cost equals the total revenue. You know how to calculate profit? Profit equals total cost minus total revenue. If these are equal, what's profit? Zero. So I don't want to harvest here. I want to have a lot less effort and harvest where I'm actually making money. So to continue to fish is not a good idea because it depends on the stock of the resource. That's in the underlying picture. If I were to take the slope of the total cost, I would get the price or the marginal cost. If I take the slope of the total revenue, I get marginal revenue. So it's where the slope of this line is equal to the slope of this line. So, somewhere in here. At this point, this is the total revenue and this is the total cost. So this is where you have maximum profit. You want to make the greatest difference between total cost and total revenue. And the same way of saying that is thinking at the margin. The marginal revenue, the extra money you're putting in your pocket, equals the marginal cost. The cost that's going out of the money that's leaving your pocket. So when those are equal, you have maximum profit. Before that point, you're getting more and more revenue, even though costs are rising. After that point, you're actually losing money. Okay? So you've got the same kind of thinking. You've got production function. We know what's happening to the fish stock, assuming we know. And we know what costs are and we know what revenues are. When we add those to the picture, we can come up with an economically sustainable point of production. And we can also be sure that it is biologically sustainable because that's built in. We're not overfishing, we're not at this point such that the stocks are going to crash. So what's the problem with this picture?
Nobody
Pardon?
that's all.
They just fish and that's all? Okay, but why? Why do they do that? No, why? Why would you fish? Because if they take too many fish today, they're not going to have a job tomorrow. So why do they do that?
They're just thinking in the short term.
I know they do. But why? Yeah, they're thinking in the short term. But why would they put, like, why would reasonable people, rational people, put themselves out of a job?
Because if they don't catch the fish,
Yes.
then someone else will.
Right. They do not have an incentive to stop fishing at this point. They need to get as much fish as possible because if they don't, some other fisherman will, family. And so what this picture shows is a fishery where, one, we know what the fish stock is, and we know it's healthy, and we know that the growth is going to continue like this, right? There's no risk in this picture. We don't know about disease or, you know, how climate change might affect fish, how an oil spill might affect fish. And so because of that, I mean, this is perfect information. With perfect information, we can be reasonably assured that we're not going to run out of fish. The other thing is, if this were a lake fishery and you were able to police the people who fished, you gave them permits, you could check on them, you could measure the fish, then you have some jurisdiction over the fishery. If it's the ocean and you go outside the 3-mile limit, who owns the fish? Nobody. You do once it's dead and in your boat. But up to that point, you can't have France come along saying, hey, you can fish, these are fish, you know. And the big turbot, what was it, the turbot, whatever, wars there a little while ago, France and Spain and Canada. There's no ownership of those marine resources. And unless you have ownership, which is the subject of the next module, I guess, then you can't be guaranteed in this picture either. Okay? Same in forestry. If you don't have ownership of that forest land, just cut it and move on, because it's not in your best interest economically to plant the trees for somebody else to harvest. So ownership is key. Okay? So you're right when you say people fish too much, but the reason is because they have an incentive to fish, right? I think I broke my own record. It's like 7 minutes after the hour. Okay, does anybody have any questions? Or you just want us out of here? Okay, we will see you on Thursday.